Welcome to the deep dive. Today we're jumping into something pretty fundamental, wouldn't you say? The actual nature of space and time.
Absolutely. It's one of those ultimate questions in physics. What is the fabric of reality, really?
Because we've got these two incredible theories, right? General relativity.
Yeah, Einstein's masterpiece. Explains gravity, the cosmos, stars, galaxies, sees space-time as this smooth, continuous sheet.
Like a trampoline bending under planets and stars.
Exactly. But then you have quantum mechanics.
Which is all about the tiny stuff, atoms, particles.
Right, and down there, everything's, well, different. It's chunky, it's probabilistic, uncertain, not smooth at all.
And the big problem, the core conflict we're talking about, is that these two they don't play nicely together.
Not at all. The math breaks down when you try to combine them.
So that's our mission for this deep dive. We're exploring quantum gravity, this whole quest to sort of reconcile these two views.
It's about finding a single theory that describes everything, from the smallest particle to the largest galaxy.
Okay, so Einstein's smooth trampoline. How does the quantum world mess with that picture?
Well, think about energy in quantum mechanics. It comes in little packets, right? Quanta.
Yeah, discrete chunks, not like a smooth flow.
Exactly. So the question becomes, if energy is quantized, why wouldn't space and time themselves be quantized at some incredibly tiny level?
You mean like pixelated?
Sort of, yeah. Instead of that smooth silk sheet, maybe if you zoomed in far enough, you'd see it's actually made of tiny, indivisible units, fundamental building blocks.
And this breakdown, this conflict, it's not just theoretical, is it? It matters in extreme places.
Oh, definitely. Inside black holes or right at the Big Bang, those are places where you have immense gravity acting on incredibly tiny scales. You need both theories to work together there.
But they contradict each other. You get these impossible answers, like infinities.
Which tells physicists, fundamentally, something's missing in our understanding. That's the driving force behind quantum gravity.
So this idea that space and time are made of tiny chunks, that's the core idea.
That's one of the key insights, yeah. Zoom down past atoms, past everything we know, to this theoretical smallest possible scale, the Planck scale. The idea is that their smoothness dissolves.
Okay. And if space is quantized and gravity is part of space-time, according to Einstein, does that mean gravity itself should be quantum? Like have a particle?
That's the prediction. Just like light is made of photons, the idea is that gravity should be made of quantum particles called gravitons.
Gravitons. So they'd be the messengers carrying the force of gravity.
Precisely. Massless particles interacting with everything. Gravitational waves, for instance, would actually be streams of these gravitons.
But hang on, gravity is incredibly weak compared to other forces, right?
Unbelievably weak, like orders of magnitude weaker than electromagnetism, which makes detecting a single graviton, well, practically impossible with current technology.
So, if we can't detect them easily, how do scientists even test these ideas? What are the main approaches?
Good question. There are a couple of major theoretical frameworks people are working on. One is string theory.
Yes, the tiny vibrating strings idea.
Right. The idea there is that fundamental particles aren't points, but minuscule vibrating loops of string. Different vibrations correspond to different particles, electrons, quarks, and yes, the graviton naturally pops out of the math.
But string theory comes with its own complications, doesn't it? Like needing extra dimensions.
It does. Typically 10 or 11 dimensions of space-time, most of which have to be curled up or hidden somehow.
Okay, so extra dimensions and strings.
Yeah.
What's the other main contender?
That would be loop quantum gravity, or LQG. It takes a different path.
How so?
Instead of strings, LQG focuses directly on quantizing space itself. It pictures space-time as being woven from incredibly tiny loops, forming a sort of network or spin foam.
Like a fabric made of fundamental loops.
Exactly. In LQG, space isn't continuous. It has a minimum possible area and volume. There are actual fundamental atoms of space.
So, truly pixelated reality in that view. Both sound pretty mind-bending.
They are, and they lead to other strange ideas like space-time foam.
Foam? What's that?
Imagine zooming right down to that Planck scale. Because of quantum uncertainty, space-time itself wouldn't be calm and flat. It would be this constantly bubbling, turbulent sea of quantum fluctuation.
Like tiny wormholes and virtual particles popping in and out of existence constantly.
Yeah, John Wheeler's idea. A boiling quantum foam underlying the smooth reality we see. It's like the surface of the ocean looks smooth from afar, but up close it's all waves and froth.
Wild. So if direct detection is hard, Physicists must be looking for indirect clues.
Absolutely. They look for tiny anomalies in light from distant cosmic events, or maybe subtle signatures hidden within gravitational waves detected by observatories like LIGO and Virgo, looking for those quantum gravity fingerprints.
So this whole quest, this quantum gravity search, it's really about trying to read the universe's deepest source code.
You could put it that way. Understanding it is key to truly grasping the Big Bang, what happens inside black holes, the ultimate fate of the universe.
And maybe even finding out that space and time aren't fundamental at all.
That's a possibility. They could be emergent properties, like wetness emerging from water molecules, something arising from a deeper, purely quantum reality.
Perhaps reality is fundamentally information, or like a giant quantum computer processing itself.
The possibilities are staggering. We don't have the final answer yet, but the search itself is pushing the boundaries of what we know.
It really makes you think. So for you listening, here's something to ponder. Do you feel space-time is ultimately smooth, the way Einstein described it? Or do you think it's fundamentally chunky, pixelated, like quantum mechanics seems to suggest?